Alright, welcome back to Meteorology 101. In this video, this is going to be, I believe, the last part of the Physics 1 study series. So we're going to cover heat, phase changes, moisture parameters, adiabatic process, and the pseudo-adiabatic process. So some of this gets a little complicated, a little tricky with the physics, but I'm going to do my best to explain it to you. So just bear with me on some of these parts, and let's get started. Alright, heat. Heat is a form of energy transferred between systems by virtue of their temperature differences. It's expressed in joules, equal Newton meter, and calories are commonly used. 0.1 calories equals 4.186 joules. Heat added to a system can raise the temperature or change the state of substances in the system. So, in our case, if you add heat to a system, our system is the atmosphere, then you increase the temperature. Dew point remains constant, then that air particle will get drier. So it can cause moisture to evaporate. So it causes the change of state within the system. So it causes a liquid to change the state to a gas. That's just an example. Types of heat. There's sensible heat. This heat can be felt and measured with a thermometer. Adding or removing heat causes a change in temperature and can change the sensible heat of the system. The equation to calculate heat is Q equals mc sub P delta T, where Q is heat added or removed, equal to the change in the sensible heat. M is the mass, C sub P is the specific heat. Amount of heat needed to raise the temperature of 1 gram of a substance, 1 Celsius degrees. And the change in temperature is equal to the final temperature minus the initial temperature. Delta T is T final, sub-final, minus T sub-initial. So whatever temperature you start with minus the temperature you ended with, that is a change in temperature. Now, not a lot to really have to study or remember here, but like the main point to get out of this slide is the specific heat values on the bottom. Land is 0.33 calories per gram Celsius degrees, and water is 1 calorie per gram. Now, 0.33 calories for land, 1 calorie for water. That will show you that land heats and cools approximately 3 times faster than water. So water is less dense, so it takes longer to heat. Land is more dense, so it heats and cools faster. So if you take a ball of dirt and you heat it up, it will heat a lot faster just because of the density. Throw it in the water, it will sink, so it's more dense than water. But you take a ball of dirt and heat it up, like I said, it is more dense. So the heat transfers through the molecules faster and it will heat up faster. So the other thing to remember from this is with the land heating and cooling 3 times faster than water is like in Florida, being a peninsula, the land heats up, then heat rises, and then allows the cool air from the water to rush in, and that creates a sea breeze. And then when it cools off at night, if it's a clear night, the land cools faster, and then that creates a higher pressure and develops a land breeze. Latent heat is the energy required changing a substance, in our case water, from one state or phase to another. Water can exist in a liquid at temperatures above 0 degrees and a vapor temperatures above 100 degrees. When latent heat is absorbed by water, all heat is used by the phase change. The molecules are taken to a higher energy state. None of this heat is used to change the temperature. If the heat is absorbed by water, the water evaporates, then that gets hotter, so the molecules move faster and there's more energy, so it takes it to a higher energy state. That's an easier way to remember that. When water is converted from a liquid to a vapor, the vapor molecules remain at the same temperatures as a liquid form. This release in latent heat will cause the molecules of water to return to a lower energy state. So as it evaporates, evaporation is a cooling process. So when As it's a cooling process, it cools off the air around it, and then the molecules slow down, and that takes it to a lower energy state. That's the way I remember that. Just remember, evaporation is a cooling process. The released energy can be used to increase the temperature, sensible heat, the measurable heat of the surrounding air. So, go to a liquid to a vapor, it does heat it up, so the temperature will increase. The amount of heat absorbed in a phase change, i.e. melting, is exactly equal to the amount released in the opposite phase change. And heat absorbed from the surrounding air will decrease the air temperature, i.e. freezing, and latent heat is conserved. That remains constant. So, like I said, remember, melting is a heating process. Evaporation is a cooling process. So, if you, I got a chart coming up. If you remember those phase changes and how, if they're releasing heat or absorbing heat, that's going to help you out with remembering what's happening to the surrounding air. So the changes, types of phase changes, the changes which require heat go from low to high energy state. The water molecules absorb energy. So as they absorb energy, heat up, they move faster, so they go to a higher energy state. The changes include melting, conversion from ice to a liquid, evaporation, conversion from a liquid to a vapor, and sublimation is a conversion from ice directly to a vapor. Changes releasing heat go from high to low energy state. Energy is released by water molecules and can be used to heat the surrounding air. And these changes include freezing, the conversion of liquid to ice, condensation, the conversion of vapor to a liquid, and deposition is a conversion from vapor to an ice. Just going straight from a vapor to a solid. Changes of state, here's the chart. If we go from gas all the way to a solid, then if you look at the bottom on the dash line, heat is released to the surrounding atmosphere. So you release that heat as a vapor. The heat's released. The water droplet cools all the way to, it's not even a water droplet, it's just gas. Cools so fast it just freezes. And then from a solid, it skips the melting phase, going to a liquid, and the ice just evaporates. And that is heat absorbed from the surrounding atmosphere. So the heat is absorbed so fast it just evaporates the ice. So a good example of that is dry ice. And then the equation for latent heat is Q equals mL. Q is the latent heat, either absorbed or released. Mass is the mass of the water changing phase, and L is the latent heat constant for each type of phase change. So I do have the equations here for latent heat evaporation, latent heat of fusion, latent heat of sublimation, and then there's a note on the bottom says that L sub S equals L sub V plus L sub F, and that is the latent heat of sublimation equals the latent heat of evaporation, of vaporization, plus the latent heat of fusion. So indicating that the amount of heat required to sublimate ice equal to the amount required to melt it and then evaporate it. The units are joule, and heat is directly proportional to both mass and latent heat constant. The greater the mass, the greater the amount of latent heat involved. The lower the latent heat constant, the lower the amount of latent heat involved. So I guess the biggest thing to get out of this is the amount of heat required to change a phase state from one phase to the other. If you went from vapor to a liquid to freezing, basically the energy it would take to switch from a vapor to a liquid to a solid, that's the same amount of energy as if you were melting, or as if you were changing that phase to a liquid and then to freezing. That's pretty much what to get out of this. I know it's a little tough for me to explain, but hopefully I helped you out a little bit there. So moisture terminology, dry air, air that contains absolutely no water vapor. That's completely dry air. moist air, there are two types of moist air, and that is unsaturated, which the air contains less water vapor than it is maximum possible, less than it can hold. And then the second is saturated air, which contains the maximum amount of water vapor possible. Saturation is a state of equilibrium. The amount of water vapor in the air is constant, but water molecules are continuously being evaporated and condensed. To maintain a saturated atmosphere, every molecule of water evaporated and one is simultaneously condensed, resulting in no change of energy. So, as in an air partial, if one molecule is evaporated, one is being condensed. That's the equilibrium. Moisture variables, absolute humidity is the density of the water vapor. The maximum value of the surface to 5,000 feet above ground level is reported in grams per cubic meter. The higher the absolute humidity, the lower the contrast between the target and the background for infrared sensors. So it's important for electro-optics. So depending on the humidity of an object, how it's going to contrast with its background looking through electro-optics. Relative humidity is what we use in weather. It's how we report humidity. It's relative humidity, and it's a ratio of the actual amount of water vapor to the saturation value and expressed as a percent. Relative humidity is dependent upon the temperature. Generally, the higher the temperature, the lower the relative humidity. And the equation for relative humidity is R equals water vapor content over water vapor capacity times 100. So how much water vapor is actually in that parcel? It would be half of it saturated. It hasn't reached saturation, but it's 50% saturated, then it's 50% humidity, relative humidity. That's what we use for weather, how much water vapor is in the air. Getting to the relative humidity of around the 60s, 60, 61 degrees, that is when you start feeling uncomfortable. All right, dew point temperature. The dew point temperature is relative humidity at which saturation will occur when the air is cooled at a constant pressure and with no change in moisture content. So if the pressure were to change, uniform cooling would not take place. The air temperature would change due to pressure changes. It is dependent only upon the amount of water vapor in the air. If the temperature is the same as the dew point, then the relative humidity is 100%. So dew point is simply the temperature that an air partial would have to cool to become saturated, to reach saturation. So your temperature, that's what I got on the last slide. We said, if the temperature, typically the higher the temperature, the lower the relative humidity. So if you take the temperature and the dew point and you have a wide spread between the two, you have dry air. If they're close together, then you have moist air. So the relative humidity is higher. Dew point depression is just simply the number of degrees of difference in temperature between the temperature and the dew point. So if the temperature is 50 degrees, your dew point is 46 degrees, you have a dew point depression of 4. That's the difference. Dew point temperature, like I said, is simply what the temperature of the air has to cool to before it becomes saturated. The wet bulb temperature is usually, it lands between the temperature and the dew point. So the wet bulb temperature is the temperature to which air is cooled by evaporating water into the air until saturation occurs. The latent heat evaporation comes from the air by decreasing the sensible heat, so it gets cooler. So evaporation is a cooling process, measured using a wet bulb temperature. The wet bulb is covered with a cloth over which air is drawn. When air is in contact with the bubbles, become saturated, so they're covered with a wet cloth. And then we used to do this as a weather observer. We had a sling psychrometer. There was two thermometers. One had a wick on it, just a cloth over top of it, and we would wet that cloth, and then we would take that sling psychrometer and spin it around for about 30 seconds until our temperatures became steady, and then we would get the dry bulb and the wet bulb temperatures. So wet bulb temperature always between the dew point and the dry bulb. The ambient air temperature, so the regular air temperature, it's always between those two. Well, the virtual temperature is a temperature that dry air would have if it were the same density as moist air. Moist air is less dense than dry air. So the virtual temperature is always greater than the actual temperature and directly proportional to temperature. So if temperature goes up, the virtual temperature goes up. The virtual temperature is directly proportional to 1/6 of the mixing ratio. And we covered that on the SCOT with the mixing ratio lines. And then temperature is the larger, if it has a larger effect on virtual temperature than mixing ratio does. The equation is T sub V equals T plus W over 6, where T must be in degrees Celsius. W is the mixing ratio. It must be in grams per kilogram. So this, like I said, it's just a virtual temperature. Just pretend if the dry air was the same density as moist air, then that's what the temperature would be. So really, I wouldn't think a lot into the virtual temperature. So the adiabatic process. The adiabatic process occurs when no heat or mass is exchanged between the system, a partial of air, and its surroundings. So a lifted air partial will expand and cool, and a sinking air partial compresses and warms. Any condensed water, deposited ice produced during lift remains in the partial, and latent heat released remains in the partial. Everything remains in that air partial if it is forced up by an adiabatic process, say forced up adiabatically, orographically, or by a front. Remains in the adiabatic process all moisture, evaporative cooling, compressing warm, descent, compression, warmth, everything remains in that partial. Now the process is reversible. A lifted or sinking partial returned to its original position will have its original temperature and dew point. All right, so the dry adiabatic rate. In unsaturated air, the temperature of a partial will change 9.8 Celsius per kilometer. As air cools, the temperature approaches the dew point. So air rises, expands, cools, approaches the dew point temperature. The temperature of the dew point, once the partial is saturated, the air no longer cools at the dry adiabatic rate. Now it has to cool. If it continues to rise and cool, it would cool at the moist adiabatic rate. Saturation or moist adiabatic rate. So when it's saturated, in saturated air condensation, and saturated air condensation and thus latent heat release occurs as air is lifted. The heat is released, it's a cooling process, it's cooled further. Latent heat release during condensation acts to heat the partial. So as the cooling process takes place, the heat is released and heats the air within that partial. So it releases that heat and has to go somewhere, so it stays within that partial. Therefore, the temperature of the saturated air decreases slower than with unsaturated air. The rate of cooling is not constant, but averages 6 degrees Celsius per kilometer and approaches the dry adiabatic rate at cold temperatures, low moisture content. So colder air holds less moisture, so it's a lower moisture content. So the rate of cooling is approximately 6 degrees per kilometer. All right, adiabatic ascent. The rising partial is unsaturated air. So the rising partial of unsaturated air will cool at the dry adiabatic rate until the temperature reaches the dew point. From that point, both the temperature and the dew point will decrease at the saturation adiabatic rate. The dew point cannot be greater than the temperature. So both the temperature and the dew point will decrease at the saturation adiabatic rate. On ascent. Adiabatic descent. For a saturated partial to descend and warm according to the saturation adiabatic rate, there must be water available for evaporation. Once the excess liquid in the partial is evaporated, the partial will warm according to the dry adiabatic rate because you're no longer saturated. So you start on the moist adiabatic descent, water evaporates, you're no longer saturated, now you go dry adiabatically, and the dew point will, at the dry adiabatic rate, the dew point remain constant. So the dew point remains constant through that process. A partial of air descending at saturation adiabatic rate warms more slowly than the unsaturated air. Latent heat required to evaporate the water in a partial is taken from the partial air. So the latent heat required is taken from it absorbs that heat. So that's where the warming is. Now the atmosphere around it is the temperature's decreasing, actually cooling. Results in decreased sensible heat of the partial. So overall, that water is that partial that is descending and warming is absorbing that heat from its surrounding area and actually cools the partial, and thus decreasing the warming of the partial. So on the adiabatic process, it starts at the surface at A. We're going from A to G. So if you look at the top right corner, there's no change from A to G. What happens is this air partial, all moisture content, and then everything in that partial stays in that partial. It doesn't mix with the outside surrounding environment. So 30-degree temperature with a 10-degree dew point. Dew point's remaining constant within that partial. Now, as the partial rises, it expands and cools. Now your temperature drops. Once that temperature drops to the dew point, then you become saturated. So you can see at C, we are 10 degrees Celsius. We had a 10 degree Celsius dew point. The temperature reached 10 degrees. Now we became saturated. Now there are clouds over the mountains. So as this continues to push over the mountains to the other side and then starts to descend, then at the top we reach 4 degrees Celsius. We're 100% saturated. Even at C, from C all the way to E, we're 100% saturated. Then we start to descend. We start to warm, and we still remain 100% saturated until we get 2 kilometers down to E. Then our temperature increases, compresses and warms, increases to 20 degrees. Now our relative humidity drops. It's compressing and warming. So it's warms the surrounding air, reaches that temperature, and then continues for the last kilometer and reaches 30 degrees and remains at a dew point of 10. So everything within that air partial remains in the air partial on the adiabatic process. So 9.8 degrees on average on the ascent, 9.8 degrees on the descent. We just rounded to 10 to make this easier to calculate. And like I said, where the temperature to dew point, we end up at, when we end at G, we end up with the same temperature and dew point on that partial as where we started. That is the adiabatic process. The pseudo-adiabatic process, all condensed water deposited ice, which takes place during lift, is assumed to precipitate out of the partial. Still, no heat is exchanged with the surrounding air. The process is not completely adiabatic because mass, the precipitation, is released to the environment or surrounding air. The heat released during condensation remains in the partial and acts to warm it. So it acts in the partial but not the surrounding air. The pseudo-adiabatic descent, sinking air warms at the dry adiabatic rate because there's no liquid water in the partial to evaporate. So the sinking air warms dry adiabatically because the water, it's not saturated, so it has to go dry adiabatically because there's no liquid in it, because it's already been poured onto the pseudo-adiabatic ascent. Now it's rained itself out. If you see a thunderstorm actually forming up on the windward side of the mountains, now the air is forced up. That's your orographic lift. It's just like a frontal lift. It's a mechanical lift, and then cools, reaches saturation, precipitation starts, it rains itself out, gets to the top of the mountains, comes back down, and it's dry. Now it has to descend on the dry adiabatic rate because there is no more liquid that was dumped out into the environment. But those temperatures, that rain was dropped out, but it never evaporated, never exchanged with the outside surrounding air, so it didn't change the environment. This is basically just a cell or an air partial within itself, just like the adiabatic process. So here's the chart for that. We start at 30 degrees temperature, 10 degrees dew point. we're not saturated. As we go up 1,000 kilometers, then, or go up 1 kilometer, then our temperature drops 10 degrees at 9.8 approximately. We drop to 20. Go to C, we drop to 10. Now we are saturated, and then that's when the precipitation process starts. We get up to D, we're still to the -4, the 4 degree temperature, -4, a 4 degree temperature and 4 degree dew point. Now we're at 4 degrees on temperature and dew point. And then we start to compress and warm, but now all the precipitation, the moisture is out of this, it's gone, and now the air partial falls dry adiabatically and increases 10 degrees per 1,000 kilometers. So we have a net warming and drying from point A to point G, and an example of this is Chinook Warming. Now this is, you can actually get a lee side low. The air partial rises up, precipitates, rains itself out, then the air comes over the mountain, then starts to warm and compress on the other side of the mountain, and actually it can warm enough to create a lower pressure and actually create a low side trough. So I think we're finished with this. This is the final slide. So if you have any questions, put them in the comments. Keep interacting with the videos, and I'll keep them coming out. Thank you for watching, and get your head in the clouds.